Voyager 1 is currently over 15 billion miles from Earth, drifting through the dark void beyond our solar system. It operates on a 1970s microcomputer possessing less memory than a modern wireless car key fob. Commands beamed from Earth travel at the speed of light, taking over 22 hours to cross the immense distance. A simple confirmation signal requires another 22 hours to travel all the way back home. When that signal hits the 70-meter parabolic dish in Canberra, Australia, its power is measured in attowatts. That incoming signal is a billion times weaker than the energy needed to run a digital watch. Engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, monitor this faint whisper every day. They read diagnostic data generated by hardware built before personal computers or the internet were ever invented. Launched on September 5, 1977, Voyager 1 was originally assigned a 4-year mission to explore Jupiter and Saturn. It has now defied cosmic conditions to remain continuously operational for over 46 long years. There are no modern microprocessors, no flash memory cards, and no automated diagnostic software aboard the probe. Every routine relies on custom assembly language executing from a primitive magnetic core memory system. Outside the titanium hull, interstellar space rests at 3 degrees above absolute zero. Inside, heat generated by decaying plutonium keeps basic electronic circuits barely warm enough to process instructions without freezing solid. Voyager 1 is now the most distant human artifact in history, moving outward at 38,000 miles per hour. Yet every byte of scientific data it collects must still be managed by engineers back on Earth. In 1977, engineers equipped Voyager 1 with 3 separate dual-redundant computer systems. The computer command system manages spacecraft sequences, while the flight data system formats scientific measurements for transmission across space. Total combined memory across all onboard computers amounts to approximately 68 kilobytes. A single low-resolution digital photo on a modern phone contains over 50 times more data than Voyager's entire memory bank. Programming required engineers to manually write raw assembly code tailored to 18-bit computer memory words. A single misplaced bit could lock up the computer permanently, with no physical way to press a reset button. Onboard electricity does not come from solar panels, which are useless in deep space, but from 3 nuclear generators. These radioisotope thermoelectric generators house ceramic spheres of plutonium-238 dioxide enclosed in iridium heat shields. As the radioactive plutonium decays naturally, it generates heat that thermocouple junctions transform into electrical current. At launch in 1977, the 3 onboard generators produced roughly 470 watts of continuous electrical power. Radioactive decay follows strict physical laws, giving plutonium-238 a precise half-life of 87.7 years. Coupled with the degradation of the thermocouples, available power drops by 4 watts every single year. To conserve precious electrical current, mission controllers systematically turned off non-essential systems over the decades. In 1990, engineers commanded Voyager 1 to turn off its cameras permanently to save power for instruments. Before the cameras went dark forever, Voyager captured the iconic pale blue dot photograph, showing Earth as a single pixel. That final image marked the end of Voyager's visual era, shifting focus entirely to fields and particles. For decades, astrophysicists debated the location of the heliopause, where solar wind yields to interstellar space. This boundary defines the turbulent outer edge of the giant magnetic bubble inflated by our Sun. On August 25, 2012, Voyager's instruments recorded a sudden drop in solar wind plasma density. Simultaneously, detections of high-energy galactic cosmic rays jumped dramatically, proving the probe had crossed into true interstellar space. Popular headlines announced that Voyager 1 had left the solar system, but that common claim is scientifically incorrect. Gravitationally, the solar system extends to the outer edge of the distant Oort cloud, far beyond the heliopause. Voyager 1 will not reach the inner boundary of the Oort cloud for another 300 years. Coasting entirely through that vast shell of cometary debris will take the spacecraft nearly 30,000 years. Entering interstellar space presented extreme power challenges, forcing controllers to turn off internal instrument heaters. Science instruments were exposed to temperatures far below the structural limits established during ground testing in the 1970s. Remarkably, the magnetometer and cosmic ray instruments continued delivering precise scientific data despite the freeze. Electrical components function perfectly at temperatures 40 degrees Celsius below their certified operational ratings. By 2023, total power generation had dropped below 230 watts, less than half its original output. mission managers were forced to disable secondary heater circuits, rationing remaining power exclusively for key sensors. Operating on a tiny energy budget, Voyager 1 became humanity's only direct source of data from interstellar space. Every measurement of galactic magnetic fields provided scientists with insights never before achievable from Earth. In November 2023, the faint signal received from Voyager 1 suddenly lost all readable structure. Instead of organized telemetry packets, the probe began transmitting a deadlocked, repeating string of binary ones and zeros. The flight data system was still operating, but it could no longer execute its primary software code. Without usable telemetry, controllers could not read instrument data, assess power levels, or confirm spacecraft orientation. In March 2024, engineers at Jet Propulsion Laboratory sent a specialized diagnostic command across space. They requested a complete memory dump from the flight data system, waiting 45 hours for the reply to return. Analysis of the 22,000 memory words revealed the exact cause of the critical breakdown. A single memory chip, representing just 3% of the flight data system's total capacity, had suffered hardware failure. The corrupted chip contained crucial code responsible for formatting telemetry data before radio transmission. Replacing the damaged hardware across 15 billion miles was impossible, meaning the entire mission depended on a remote software patch. Engineer Bob Rasmussen and the mission software team devised a complex fix to bypass the dead chip. They divided the affected software code into smaller sections, fitting them into healthy memory locations elsewhere. On April 18, 2024, NASA transmitted the modified assembly instructions across 15 billion miles of void. 2 days later, readable telemetry returned to Earth, confirming that Voyager 1 had been restored to full functionality. The recovery proved that engineers could still modify late 1970s software operating in deep space. However, while code can be patched from Earth, no software update can replenish the probe's declining nuclear energy supply. The continuous decay of plutonium-238 imposes a strict physical limit on Voyager 1's remaining lifespan. With electrical power decreasing by 4 watts each year, mission controllers face inevitable decisions regarding instrument shutdowns. Over the next few years, engineers will systematically turn off the remaining active scientific sensors one by one. Eventually, only the central engineering systems will receive enough power to keep the radio transmitter alive. Between 2025 and 2030, electrical output will drop below the absolute threshold needed to operate any system. At that point, Voyager 1 will cease all operations, becoming a silent, dormant object in interstellar space. Its radio transmitter will turn off forever, ending more than half a century of continuous communication with Earth. Yet the physical spacecraft will continue coasting through space at 38,000 miles per hour indefinitely. Bolted to the spacecraft chassis is the Golden Record, a gold-plated copper phonograph disc. It contains images, greetings, and natural sounds from Earth, protected by an aluminum cover coated with ultra-pure uranium-238. The record is engineered to survive cosmic radiation and micrometeorites for over 1 billion years. It serves as a permanent time capsule, preserving a physical record of human civilization long after our sun changes. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of the star AC plus 79 3808 in the constellation Camelopardalis. Long after humanity's radio transmissions vanish from the cosmos, this metallic Voyager will drift through the stellar dark, carrying our quiet message across the silent galaxy.